All right, we've got a bit different problems here in section 8.8. This is Taylor and Maclaurin series, page 802. Let's tackle 2 for the price of 1, and that's doubly free, number 18 and number 19. So, the first problem is f of x equals e to the 2x and c equals -1, and we're supposed to use the power series representations of functions established in the section to find the Taylor series for this function centered at -1. So, in some ways we're supposed to cheat. We're supposed to use the Taylor series we already have in this section. Which ones do I have? Well, remember on page 795 we have this, and if I'm trying to deal with the function e to the 2x, it's a pretty good guess that I'm going to be using e to the x, right? So that power series, this is the one I'm working on, and the one that I have from the table on page 795 is e to the x equals the sum n equals 0 to infinity 1 over n factorial x to the n. And the nice thing is the domain of this is the best case, is -infinity to infinity, so the radius is infinity. So that'll work in our favor. Pretty much any way I tweak it, I'm still going to have radius infinity. So what shall I do? First off, you notice that it's 2x, not x. Well then, how do I take e to the 2x? Well, this is a variable, right? So I could substitute in 2x into the place of x. What do I get out? I get out 1 over n factorial 2x to the n. That is just exceedingly convenient, right? Now, first off, you recognize that doubling my x sizes, since my radius was infinity, it's still infinity. I divided that infinity by 2. Isn't that grand? Okay, second, notice that if you want this to still be a power series in x, you might, one way to sort of think about that is you might just take off 2 to the n over n factorial x to the n. Now this is, so those are the coefficients. N factorial still grows a heck of a lot faster than 2 to the n. And I've still got this. The problem is this is still centered at 0, right? You could write this as x minus 0 to the n. How do I get it centered at -1? So somehow it's supposed to be x minus -1 or x plus 1. How would I go about doing that? Well, here's the catch. Somehow or other, where I have x in this, I need x plus 1. Well, how do you deal with that? Well, how about we just put in x plus 1 instead of x? So I have that. Now, you might say I just screwed up my left-hand side. Hold on with me for a second there. But the right-hand side is at least centered at the right place, right? We agree that this is a power series centered at -1. Isn't that grand? And you say, yes, but that is not e to the 2x. And you're right. However, here's the thing. Since this, you could write it as e to the 2x plus 2, you can actually distribute that. That's e to the 2x times e to the 2, right? A sum in the power is the same as multiplying in the basis. Okay, so now this is just a constant times what I want to have. So how do I get rid of that constant over there? I divide by that constant. I'll divide both terms by e to the 2. So e to the 2x equals n equals 0 to infinity of 2 to the n over e to the 2 times n factorial x plus 1 to the n. Is that not cool? Wow! It's e to the 2x, it's centered at -1, and the radius is still infinity. There we go. Oh, and we get 2 for the price of 1. Now, why did I put in 2 for the price of 1? Because this one's really cheating. That one at least I had to do a little bit of work for. This one, you might notice, back on page 795, I have, hey, cosine with a radius of negative infinity, sorry, the radius is infinity, the interval is negative infinity to infinity. That works great. So cosine, I already have this power series description. Right? Well, what's missing? It's centered at 0, so I've already got that. I have this nasty extra x squared. Well, how do I get an x squared? Answer, you multiply everything by x squared. So, x squared cosine x equals the sum from n equals 0 to infinity of negative 1 to the n, 2 to the n, 2 times n factorial, x to the 2n plus 2. Everything gets an extra times x squared. Notice this is still a power series, still centered at 0, and the radius is still infinity. Isn't that grand? There you go.